Hello, everyone. Good morning, and welcome to our virtual Icassp tutorial on machine learning and wireless communications. I'm Yunina Eldar from the Weizmann Institute in Israel, and this tutorial will be delivered by Nir Schlesinger, my brilliant postdoc, who will soon be starting a faculty position at Ben-Gurion University in Israel, and Professor Vince Poor from Princeton, who all of you know and admire. Before we begin, we'd like to thank the organizers and the tutorial chairs, Sabrina and Philip, for inviting us to give this tutorial. Of course, we were very much looking forward to seeing you all in person in Barcelona and being able to have an interactive tutorial, but very thankful to everyone involved for giving us an opportunity to meet and exchange ideas, even under these difficult circumstances. This is, of course, the first time any of us are giving a virtual tutorial, and probably the first time you're participating in one. So we hope we still be able to do a good job in explaining the ideas and getting you excited about the potential of deep learning and wireless communication, which we really believe is an extremely important and exciting area and opportunity. Our focus in the tutorial today will be on the unique opportunities offered by the interplay between machine learning and wireless communications, where we're going to consider both the theoretical ideas and also show various applications to many interesting communication problems, which will hopefully demonstrate the many ways in which machine learning can help enhance the new generation of wireless networks. We're all aware of the fact that today, a very popular approach across all data science areas are ideas based on machine learning that learn the information needed from large amounts of training data. In fact, with enough data, deep networks tend to learn almost everything and have led to the best results in various tasks like image recognition, speech translation, and many other examples which don't have good models. Now, machine learning has a very rich history dating back at least to the early 40s when McCullough and Pitts introduced the first mathematical model of a neural network in their landmark 1943 paper. In fact, the basic unit that they introduced in this paper is still the standard of reference for a mathematical description of a neuron, even in neural networks today. Now, moving ahead, in 1958, one of the first machine learning algorithms was developed by Rosenblatt, which is the well-known perceptron algorithm. And this is a method for supervised learning of binary classifiers, which is used today in many different applications, but was originally introduced for image recognition. Over the years, there were very many important developments in machine learning, leading to backpropagation and SVM in the 90s, and this really laid the foundation for modern deep learning. In terms of industry, the impact of deep learning began in the early 2000s when GPUs were developed and computers started becoming much faster and efficient at processing data. So this faster processing with GPUs processing pictures increased the computational speeds by at least 1,000 times over, for example, a 10-year span. And this led to neural networks being able to compete with other standard machine learning methods, such as support vector machines and a variety of other traditional approaches. By 2011, the speed of GPUs had increased so much that it already became obvious that deep learning had significant advantage in terms of efficiency and speed. One of the most well-known examples of the early success of deep networks is the famous AlexNet, which is a convolutional neural network that won several different international competitions in 2011 and 2012. So as we can see, in the past decade, deep learning has really revolutionized many fields with huge empirical success, especially areas where modeling is difficult and obtaining large training sets is actually feasible. Now, wireless communications also has a rich history and present. If we start by going back to the 40s, we already see early applications of commercial wireless telephone services. The first trials of cellular systems were conducted in the late 70s, with the 80s bringing commercial analog cellular technology with fully implemented standards. The real revolution in wireless began in the 90s with the advent of digital wireless networks and the introduction of GCM and roaming. This really led to a proliferation of commercial wireless technologies, such as cell phones, wireless computer networks, of course, the internet, navigation, email, music, and various different wireless connections for the laptop and handheld devices. The transition from analog to digital technology really enabled a substantial increase in voice traffic and of course the delivery of digital data, which is so important for all our modern applications like text messages, images, and various different types of streaming media. So looking back, the development from 1G to 4G and now into LTE and beyond to 5G really enabled many new and important technologies and accelerated the rate of advance. This, of course, comes with increased demands on speed, capacity, coverage, power efficiency, and costs, and leads to various system trade-offs that need to be optimized. So we've just very briefly seen the history and impact of two major technologies of the 21st century. Wireless technology on the one hand impacting the way we communicate, and machine learning on the other, which really has had a broad impact on many new technology areas. What we want to consider in this tutorial is where these two major driving forces of technology can combine and further accelerate future applications. So what we're going to focus on today are two main aspects. The first is how machine learning can be used to design and optimize communication networks, especially given the growing demands that we just talked about and the many trade-offs that have to be addressed in future networks, which lead to many system parameters that need to be designed and very complicated optimization problems. So we believe that machine learning can have a very important role here. The second aspect we want to address is how wireless networks can aid in learning by using the mobile devices as learning devices and harnessing the power of wireless communications to perform very efficient learning at the edge in a distributed fashion on the user device. So here we're going to use the wireless networks as a learning mechanism. So let's now go ahead and consider briefly these two aspects, which we're going to expand on throughout the tutorial. So first, let's talk briefly about how we can use machine learning to design wireless systems. Now, typically when we think about standard signal processing and communication methods, they're typically designed based on models. So we're going to start with some physical model or a good approximation of a model, and we're going to use that to develop different optimal algorithms. This allows us to easily incorporate, for example, different domain knowledge and structure into the methods. So if we look at a standard wireless problem where we're going to assume some model for the transmitted data, the symbols here S, and then we're going to assume some model for the channel, which we're going to use at the receiver in order to design an optimal method to extract these bits that we transmitted from the received output denoted here by Y. So this standard approach heavily relies on our ability to estimate or approximate the various parts of the system, such as the channel and the noise model. Now, once the model is known or estimated, we can use it to develop various different optimal methods under different criteria, and we could also use the model to properly analyze the performance. So the advantage, of course, is that this leads to a very systematic way to design systems, and also often leads to methods that have controllable complexity. So to be a little bit more specific, we're typically going to start with a simplifying model to write down an input-output relation for a channel. So a common choice is, of course, the very well-known linear Gaussian model. In this model, we're going to assume that our received signal, which is denoted here by Y, is going to be some linear combination of the transmitted signal, denoted here by S, and H here is going to represent the channel. And to that, we're going to add some Gaussian noise. The problem is, of course, that this model may not be exact and it may not take into account various different channel distortions, which could be very difficult to model. The other difficulty is that in this approach, we're going to assume that the channel, which is represented by this matrix H, is known, which means that in practice, we have to accurately estimate it and track it when the channel changes, and this leads to a large overhead. In addition, besides the overhead, we're always going to have some tracking error, which can deteriorate performance and may be very hard to analyze. So this is exactly where we hope machine learning can help us. We know that machine learning does not rely on model knowledge, but rather learns it from the data directly, which would really help address the modeling issues. On the other hand, in communication systems, there's still a lot of known structure since many components of the system are designed by strict protocols, and many parts of the system can actually be accurately measured. So this leads to what we're going to call throughout the tutorial model-based deep learning, which are basically methods for combining learning with known models. And this is going to be an important theme throughout the tutorial today. So what this will enable us is to develop methods that on the one hand rely on structure when it's known, but on the other hand allow us to learn the unknown system parameters directly from the data. Let's now move on to the second aspect of the tutorial, which is using wireless networks to enable efficient distributed learning. One of the key components of deep networks is having available to us large labeled training sets. Now, very often, this data is coming from distributed users, such as images taken with a cellular device, data coming from smart vehicles, and data coming from different tablets. The training, of course, needs to take all these different sources of data into account. A standard way of doing that is for each user to send their data to a joint server and then perform training on the server using all the data. In practice, this is going to mean communicating the information over existing wireless networks. Now, this in turn is going to lead to several challenges. First of all, sending labeled data to a joint server requires very large capacity since the volumes of the data are going to be very large, especially when we're talking about images and movies. This also raises huge privacy concerns. As a user, we probably don't want to share our stored images with the server that others have access to. So what we can suggest as an alternative is that instead of doing the learning on the server, which will require all the individual users' data, we can attempt to do the learning at the edge, namely on the devices themselves. In this approach, each user is going to train a local deep network based on their local data without actually sharing the data. And what they're going to share across the network are only the learned weights or gradients of the network themselves. This leads to what is known as federated learning and distributed learning, where the data remains protected and local, and what is shared are only the network updates. Of course, this has to be done in a way in which the overall learning is still optimal and such that the shared data remains private. In this framework of federated learning, wireless communications are going to play a very important role since the wireless network is going to dictate the constraints and the opportunities for this joint learning. Now, there are many opportunities for wireless methods to help in learning at the edge, including, for example, various ways to ensure privacy of the information, techniques to schedule the users, ways to harness the properties of the channels themselves to enhance the learning process, and of course, channel knowledge to mitigate different interference over the network. Clearly, communication and coding methods are going to have a large role to play when the learning itself is done over a wireless network, and this is going to be the focus of the second part of the tutorial. So hopefully, this has given you a sense of the potential of merging wireless communication and deep learning, and outlined some of the main aspects that we hope to cover in the tutorial today. Before we go ahead and jump into the details, I want to end the introduction by stating some of our goals for the tutorial. So first, we hope to expose you to some of the exciting ideas and results in this area of model-based machine learning and see the way we can impact wireless system design and next-generation wireless systems. We also hope to provide a glimpse of the really huge potential of using communication tools for learning deep networks, which is an area that is just emerging and is sure to grow in the next few years. So what would we like from you? Well, we would have wished for this tutorial to be as interactive as possible, which of course is probably very difficult under the current circumstances, but we still hope over the break we'll be able to address various questions, and if not, then hopefully offline over email, we'd love to hear your input and thoughts. And most important, we hope that despite not being able to interact as much as we would like to, we hope you'll be able to learn and enjoy this tutorial. So with that, let me end this first part by going over the detailed tutorial plan. We began already with an overview of our goals and main topics. The next part will focus on relevant background in deep learning, which is needed for the rest of the tutorial. We'll then split the remaining of the tutorial into two parts, one that is focused on using machine learning to optimize wireless networks, and one that is focused on using wireless communication to implement distributed and federated learning. So with that, I'm going to turn over the tutorial to Nir, who's going to begin by giving an introduction to deep learning.
Hello, my name is Nir Schlesinger. I am a postdoctoral researcher in Weizmann Institute, where I have the honor of working with Yonina Eldar. In the next part of our tutorial, I will survey some relevant preliminaries in deep learning. As we know, we're nowadays witnessing the deep learning revolution. Deep neural networks allow to achieve superior performance in a multitude of areas, including computer vision, speech processing, and in various problems which are difficult to tackle using conventional optimization tools. What are those neural networks? In the end, those neural networks are a concatenation of a multitude of parameterized transformations. These are divided into affine mappings, such as fully connected layers, convolutional layers, and nonlinear activations, such as ReLU and sigmoid. And by concatenating a set of those affine mappings activation, affine mapping activation, we get an overall highly parameterized function which defines the network mapping. Now, in order to determine the quality of such a network, we need to define a loss function. It can be the logistic loss or the squared loss. And we want to tune the parameters of this neural network to minimize the loss. And we do that using training, using data. How do we train using data? The common tool is stochastic gradient descent or some variant of it. Now, how does stochastic gradient descent work? Stochastic gradient descent refers to the tuning of a set of parameters, theta, which dictate a function f of theta, which in our case, the parameters are the weights of the network, and f of theta is the mapping of the network. And it does so using training data and some empirical loss function, which is defined with respect to both the parameters and the training data. Now, the goal is to recover the parameters which minimize the empirical loss. Now, if the training data are randomized from some IID distribution, then it also coincides with the statistical loss. Namely, we can replace this sum here with an expectation with respect to the distribution of the training data. How can one tune the weights in light of the training data and the loss function? One way to do so is using conventional gradient descent, which operates iteratively, and at each iteration it takes the current weights and it reduces some learning rate or step size times the gradient computed at the current weights. Now, we know that this approach will end up converging to some local minima, which will hopefully be a good minima. However, when we look at the computation here, we note that computing the gradient at each iteration, at each training point, can be very computationally complex, given the fact that the training data can be very, very large. So what is usually done is what's called stochastic gradient descent, where instead of computing the full gradient, we're just randomizing a single training labeled sample, and we're computing the gradient with respect to this sample alone. This boils down to this equation here, which is much more computationally simple compared to the standard gradient descent, but it is carried out over a large number of iterations. Essentially, we call an epoch each passing over the complete data set, over the complete training set, and we train over multiple epochs. Namely, it's repeated a large number of iterations. We don't have to just take one sample at each time. What people usually do is use mini-batch stochastic gradient descent, in which instead of taking a single sample, we're taking a batch of samples at each iteration. Now, also, gradient descent on its own is usually not the algorithm used. Some variants of it are used, like stochastic gradient descent with momentum, like RMS prop, Adam, and so on. But essentially, these are all variants of stochastic gradient descent meant to increase its convergence speed and to stabilize it. But the underlying rationale is quite similar for all those variants. Now, stochastic gradient descent deals with the need to take standard gradient descent and make it less complex by computing the gradient with respect to only a mini batch or even a single training sample at each iteration. Now, the question is, how are these gradients computed? Now, fortunately, while neural networks constitute complex mappings which can imitate a very large number of different transformations, they have a specific structure, which is this concatenation of layers, or concatenation of parameterized affine mappings. And this format, this structure, facilitates computation of the gradient because we can do that using the chain rule. In order to compute the gradient of the loss with respect to a given parameter, we just need to compute the loss with respect to the output of that specific layer, times the gradient of this specific layer with respect to that specific element. And that makes the computation of the gradient relatively simple and can be carried out using what's called backpropagation. So stochastic gradient descent combined with backpropagation allows one to tune the overall weights in light of a loss function, an empirical loss function, do it in a computationally feasible manner, and those are two fundamental tools in training deep neural networks. Now, there are various types of models for machine learning and for deep neural networks. They can be divided from a broad perspective into the following. The first is the family of supervised training models, which learn a mapping from some input space to some label space. And this is carried out by providing the network with a very large number of labeled samples. Namely, here we're showing images, and we're showing for each image, we're specifying its label. For example, these are images of mugs, these are images of hats, and so on and so on. And by doing so, we should be able to tune the network transformation to be able to carry out classification or regression or any other of those supervised tasks. There's also the family of semi-supervised learning, which are quite similar to supervised, but they combine training using some label data, some data which we know to which label it belongs, and some data which we do not know to which label it belongs. And the other family of models is unsupervised learning. Now, unsupervised learning train on unlabeled data. Namely, we only see inputs. There's no label assigned to each one of those inputs. So obviously, we're not learning here a mapping from input to label. We're trying to learn something about the underlying structure, something about the statistics of those inputs, like how to compress them, how to generate samples, and so on. So let us now review some basic conventional machine learning architectures. The first is the classification network. Classification network operates on an input, which can take continuous values, and it's a supervised training, so it also has labels, typically taking discrete values, and the output of this network is a score. We are giving a score to each possible label given this input. For example, if our label space is cats and dogs, and we see a 32 times 32 color image which looks like this, then a desirable output of a network would be that it is 3% cat and 97% dog, for example. Now, the objective, in light of which such classification networks are trained, is what's called the empirical cross-entropy, or also the logistic loss, which is given by this expression here. And the main motivation for utilizing this, or at least the statistical motivation for doing so, is that when the empirical loss approaches the statistical loss, namely, we have a very large number of IID labeled samples, then the actual mapping which will minimize the resulting loss will be the true conditional distribution of the label given the input. Namely, we will be able to utilize the output of this classification layer to implement the maximum posterior probability detector, which is known to minimize the error rate, for example. Another family of networks is what's called regression networks. Now, the difference between regression networks and classification networks is that the output here is not a score. It's an estimate of the label. So the label can now take continuous values, not necessarily discrete, but this is also a supervised setup. As an example for a network which carries out an estimation task, we can consider the case where the label space is priced in dollars and our input are some attributes of a house, and want to predict the price of this house. Now, such networks are usually trained using the empirical squared error because, again, when the empirical loss coincides with the statistical loss, what we get is that the objective is minimized by the MMSE estimate. An additional family of machine learning methods are generative networks. Generative networks, unlike classification and regression networks, operate in an unsupervised manner. Namely, there's no label here. There are only inputs. And what we're trying to do is we're trying to learn a mapping from some known low-dimensional space into the input space. So, for example, And most common example is the generative adversarial networks, which, when properly trained, can map some random noise, whose distribution we know can be low dimensional, into an image of a celeb. So it essentially learns a mapping from random noise into the domain of celebrity images. Now, there are various objectives to design generative networks. They depend on the architecture. For example, in generative adversarial networks, we have a generative networks, we have a discriminator networks, which compete, and the goal is to optimize the min-max loss. There's also the family of variational autoencoders, which are trained using the elbow, the evidence lower bound. One can also utilize flow networks, where you can actually define the likelihood as the objective. But essentially, the bottom line is that generative networks attempt to learn a mapping from a low-dimensional known space into a desired high-dimensional space. The last family of established neural network architectures are autoencoders. Again, we are dealing here with unsupervised learning, namely, we only have sets of inputs. But here what we're trying to do is we're trying to learn how to recover the input from its compressed version. Namely, we're trying to simultaneously learn a mapping of this input into some low-dimensional latent space, and a mapping from this latent space back into the input space. And by doing so, we're able to recover some compressed version, or perhaps an approximate sufficient statistic of this input, from which it can be recovered with high accuracy. Now, the objectives here vary. It can be, for example, the squared error between the reconstruction and the input, while we are fixing here the dimensionality of the latent space in the middle. And in the end of the day, those autoencoders show great capability in learning low-dimensional approximate sufficient statistics without having to explicitly specify the distribution of the input, only to provide a large number of labeled data, of unlabeled data. These aforementioned machine learning architectures allow us nowadays to achieve unprecedented empirical success in various applications. For example, generative networks are now able to generate fake faces, to spawn fake people like the ones we see here. These are all AI spawned faces. Classification networks are now surpassing human performance in classification of images. However, this unprecedented empirical success does have its challenges and drawbacks. For example, in order to achieve that, we need a large training set, we need a large computational power, and we do not necessarily understand exactly what's going on, like we see here in this comic. In the end of the day, it may just boil down to throwing a large number of training set and doing some linear algebra without necessarily being able to interpret, to understand the operation of these neural networks. Furthermore, training time can now be substantial, as we can also see in this comic, which states that the number one data scientists excuse for slacking off is, well, my model is now training. There are obviously other challenges associated with deep networks, like robustness and generalization. And in this tutorial, which is about machine learning and wireless communication, we will try to focus on two main questions. First is, can we exploit the advantages and the benefits of machine learning tools while mitigating their challenges to allow them to optimize wireless networks? In addition, we will also attempt to answer the question, which of the challenges associated with machine learning can be tackled using communication methods?
Now that we reviewed the basics of deep networks, we want to turn to discuss how we can harness their power in the context of wireless communications and see how they can help us solve difficult problems in the context of 5G and beyond networks. Let's begin by considering why we may need machine learning in the context of communications. In general, we know that when treating various design problems in communication systems, we often end up with complicated optimization problems, which can include many design variables. They may be non-convex or even untractable, and often depend on system parameters that might not be known. For example, one of the fundamental problems in the physical layer is designing an optimal receiver to detect and decode transmitted symbols. This often leads to combinatorial optimization problems and also requires knowledge of the physical channel. Now, the channel is often estimated in advance, for example, using pilot symbols, but this necessitates additional bandwidth and capacity. It requires time, and it assumes that the channel doesn't vary too quickly, which is not always practical, for example, in a multi-user environment with rapidly changing channels. In this case, estimating the channel repeatedly between all users is not going to be very practical and is going to consume too many channel resources. Another good example is multiple antenna systems, where there are many design issues related to beamforming in both the transmitter and the receiver sides, which again lead to various combinatorial problems, especially when we consider antenna selection methods, and they again will require knowledge of the channel statistics. Security and coding issues are another area where optimization is necessary and often quite complicated. On higher levels of the communication system, we again tend to end up with various optimization problems, which will involve multiple users, often discrete variables, and require knowledge of many system parameters that are not often known, such as channel gains, number of active users, user codes, timing constraints, and many more parameters. To get a better sense of where machine learning can help in communication and why it is needed, let's take a closer look at one of the most basic operations of a communication system, which is symbol detection. So in a standard detection problem, we're going to have a transmitter that wants to transmit messages or symbols to a receiver over a given channel, in our case illustrated over here, a MIMO channel. Now the transmitter is going to do that by sending a signal S, which we're going to obtain as an output Y. In order to recover S from Y, we're going to rely on a model that describes the relationship between Y and S, where the most popular model is the linear Gaussian model, in which the received signal is assumed to be a linear combination of the transmitted symbols over a block plus a Gaussian noise. Now this model is used really due to its simplicity. Under this model, there are very many well-known receivers that are optimal for different criteria. For example, we could design a detector that maximizes the likelihood of the received output Y. However, in practice, the channel may not be linear, the noise may not be Gaussian, and most importantly, the channel is often not even known, and as we alluded to already, estimating it repeatedly is going to consume too many channel resources. So this seems to be a good problem to examine and ask whether using the tools of machine learning, we can avoid knowing the channel and having to model it exactly. In general, we know that machine learning provides methods that do not require not knowing the exact model. So this seems like a very relevant area in which to apply machine learning tools. So how would we do that? Well, a straightforward idea is to just take this current receiver and replace it by a deep network that uses end-to-end training to perform the detection. However, the difficulty is that the advantages of machine learning typically come into play when we have very large training sets, which will not typically be the case in a communication environment that is rapidly changing. In such a setting, it will be impractical to collect large training sets every time the channel changes. Furthermore, as we know, in general, although machine learning methods can work very well, very little is known about their optimality properties and the quality of the solutions from a statistical perspective. On the other hand, standard communication theory provides us with methods that are optimal under various criteria and for which we can analyze the properties of the solution in a convenient manner. So this raises the interesting question of whether instead of using black box machine learning solutions that were not designed specifically for communication problems, we can combine machine learning and communication in a way that preserves some of the desirable properties of the standard communication solutions. In other words, what we'd really like is to develop learning methods that rely on well-understood models of communication systems rather than generic solutions. In contrast to deep networks, signal processing and communication are in general based on physical models. This allows us to easily incorporate domain knowledge and structure into the methods. It also allows us to perform inference with small data sets and to easily assess the quality of the output. The main drawback, however, of traditional signal processing methods is that they rely on accurate model knowledge that we already spoke about in the context of communication. And in addition, inference can often be quite slow and difficult to implement. Therefore, the question is whether we can combine the ideas of models with deep learning in order to be able to arrive at compact, interpretable, and simple to train data-driven systems. To see how we can do this, let's take a bird's-eye view on model-based processing versus deep learning. In a standard model-based method, we usually have some set of measurements y, from which we want to infer some unknown x. So in the communication context, y was our received signal, and x were the symbols we want to infer. We typically also have a model that relates y and x, and we use that to design an algorithm that determines x by optimizing some metric, which relies on this measurement and the known relationship. So here in this example, the relationship is y equals approximately g of x, and f is going to be a metric that we're going to want to optimize. When we go ahead and try to optimize f, we typically end up with a series of steps that need to be carried out in an iterative fashion. So we typically have some generic mathematical operation, and we then have a set of iterations between a generic computation and some block that depends on the underlying model. And then we typically have some mathematical operation at the end, which will give us the desired outcome x. Now, on the other hand, in deep learning, we do not assume we have a model, but instead, in some sense, we're going to perform magic in a sense that we're going to replace the model by a black box that does not know anything about the problem. Instead, it's going to obtain lots of inputs and outputs that are paired, and from then it's going to learn the parameters of a network in a series of layers that form the desired deep network. Once we get the deep network, we're going to apply this to a new input y and obtain the desired recovery x. So the question is how we could combine these two approaches, and to do that, we're going to suggest two different methods. The first is to integrate model-based methods into deep learning by relying on the idea of unfolding that was first suggested by Gregor and LeCun. The second approach we're going to use is the reverse in some sense. So we're going to integrate deep networks into existing model-based algorithms. Okay, so what we're going to do next is just briefly describe these two approaches, and then Nir is going to take over and show how both of these approaches are actually used in the context of different communication problems. So let's begin by looking at unfolding, which was first suggested by Gregor and LeCun and has gained growing interest in both the signal processing community and the wireless communication community. So the basic idea in unfolding is to take our optimization problem that we talked about before, and instead of just looking at the loop of iterative steps, we're going to explicitly write out several of these steps. So for example, we could explicitly write out 10 iterations. So until now, we didn't do anything new. We're basically just implementing an iterative algorithm. But the learning is going to come into play in the final step, where instead of implementing these iterative steps that are typically going to depend on channel parameters that we don't assume are known, we're now going to use training data to learn the parameters in each of these steps. So in this way, instead of getting a generic deep network, we're going to get a network where we have a small number of layers, and the structure of these layers follow from the optimization problem. But instead of plugging in channel parameters that might not be known, we're going to learn them from training data. So this is the general approach behind unfolding that was applied to many different problems in signal and image processing. And we have a recent review where we discuss different applications. It has also become very popular in communication networks, and we refer here to a review specifically for communication, and we'll see a few examples in a couple of slides. So this is the first approach we can use in order to use a model-based approach in the context of communication. The second approach we suggest is very different. So it's actually starting from the given solution. So starting from the generic solution that we know is good when we know the channel parameters, and then just taking the block that depends on those unknown parameters and replacing it with a generic deep network. But now this deep network is only going to be replacing a specific block, not the end-to-end solution, and therefore we still retain the structure of the well-known communication solution, but do not require knowledge of unknown parameters, which are estimated by this deep network. So this again was reviewed in a recent paper that we wrote that reviews this approach, and we're going to be talking a lot about it in the next few slides. So what we're going to do next is see how we can use these two approaches, the unfolding approach and this data-driven hybrid approach, and apply them to various different communication problems.
In this part of the tutorial, we will present some applications of deep learning in receiver design. Specifically, we will focus on the problem of symbol detection, where we have a set of channel inputs which are symbols taken values in some discrete constellation. They go through a channel and the receiver observes its channel output, from which its task is to recover the transmitted symbols, and to that aim, it utilizes deep learning techniques. We will consider three main approaches with concrete examples for deep receiver design. We will begin with the usage of established deep networks for this task. Namely, we're using a conventional neural network architecture in order to classify or to infer the symbols from the channel output. As an example, we will show the sliding bidirectional recursive neural network, which was proposed as a symbol detector designed for finite memory channels. Then we will discuss how unfolding can facilitate symbol detection using deep networks. And as an example, we will show DetNet, which was proposed as a symbol detector, unfolding-based symbol detector for MIMO channels. Then we will go into data-driven hybrid algorithms advocated earlier, showing several concrete examples: the implementation of the Viterbi algorithm in a data-driven fashion, the implementation of the BCJR algorithm, and DeepSeek, which implements soft interference cancellation for MIMO detection. Let us begin with the usage of symbol detection using established networks. So the rationale here is to replace the receiver with a conventional neural network architecture, acknowledging the fact that symbol detection is essentially a classification task. We're trying to recover a block of symbols taking values in discrete set from a channel output which may take values in continuous set. So the rationale here is to identify what deep architecture is suitable for the considered channel, which deep architecture can carry out symbol detection reliably for the considered case. Once we identify this architecture, we just need to use it as symbol detector and simply train the whole thing in an end-to-end manner. And hopefully, by showing this deep architecture a sufficient amount of labeled pairs of channel outputs and the corresponding symbol, the resulting deep symbol detector should be able to carry out inference reliably. As an example, let us consider a finite memory channel in which the channel output is some function, stochastic function, unknown function, of its last set of, let's denote by L, channel inputs. So this is a conventional finite memory channel, though notice here it doesn't have to be linear. In the work of Falsad and Goldsmith from 2018, they proposed to use an architecture which is based on bidirectional recursive neural network. And the rationale here stems from the fact that the maximum posteriori probability detector for such channels actually implements a set of forward recursion and a backward recursion in order to recover its corresponding symbols. Now, I will specifically go into those forward recursion and backward recursion later on when we speak about the BCJR algorithm, but let us at this point just say that the implementation of two-directional recursions which meet at each specific symbol allows one to implement the maximum posteriori probability symbol detector, which is a symbol detector which minimizes the error probability. So in light of that knowledge, that's for these kind of channels, the best thing to do is some forward and backward recursions. What Falsad and Goldsmith proposed to do is just to learn those recursion using bidirectional recursive neural networks. And this essentially exploits the temporal correlation in the observed channel outputs. Now, once we do that, the it allows us to exploit the channel memory without doing it explicitly. We're just utilizing a neural network architecture which is capable of exploiting temporal correlation in time sequences. In their work, they trained it over multiple channels, only once, but they did use the order of 30 million training samples in order to train this highly parameterized neural network. And what they were able to show is that for some scenarios, the resulting receiver comes quite close to the performance of the maximum likelihood sequence detector. There are several drawbacks of utilizing deep conventional architectures for symbol detection, and the most notable one stems from the fact that we're now having a very highly parameterized network with a very large number of tunable parameters, implying that you need very large training sets. In the end of the day, in the work of Farsad and Goldsmith, they used about 30 million training samples. And we know that communication channels are dynamic. So even if you train it over a set of channels, at some point the channel may change in time and you may have to retrain the whole thing, which takes considerable amount of time. Also, by using just a conventional, some sort of a black box architecture, we end up with a receiver which is quite non-interpretable. The main advantages of using this approach stems mostly from its model invariance. It does not need to impose a specific relationship between the channel output and the channel input. It does not need to know its parameters, and it hence also applicable in very complex setups. For example, in the work of Farsad and Goldsmith, they were able to apply their SBRNN-based symbol detector to very complex channels like molecular communication channels and channels in which the input-output relationship cannot be expressed analytically, but is known to obey a finite memory structure. For the unfolding case, here the rationale is somewhat different. Here, instead of trying to identify what network architecture would do the symbol detection task better, we're trying to identify an iterative optimization algorithm which is suitable for the task of symbol detection under the considered channel model. And then we fix the number of iterations and unfold each iteration into layers, just like we have here in this architecture. And once we've done that, we end up with a deep neural network which imitates the operation of the iterative algorithm, and we just train the whole thing in an end-to-end manner, again, hopefully, by showing this deep architecture a sufficient number of labeled samples, namely a pairs of channel outputs and the corresponding symbols, the resulting architecture should be able to carry out this optimization algorithm reliably. Let's see an example. The example we will discuss here is the one by the work of Samuel Diskin and Wiesel, learning to detect. This architecture is called DetNet, and it's suitable for linear MIMO channels in which the channel output is given by some metrics times the channel input plus noise. Specifically, they consider the case where the channel inputs are BPSK symbols and the channel matrix is known. So note that we're already beginning with a case in which we know the model and we know the parameters. Now, the goal here, assuming that the noise is Gaussian and IID, we know that the maximum likelihood sequence detector is simply the one which finds the minimum distance symbols. And it boils down to this optimization algorithm in which we're trying to recover the symbol vector, which after applying the channel to it will be the closest to our observed channel outputs. Unfortunately, when the dimensions of S are large, namely we have a large number of transmit antennas or a large number of transmitters, this optimization problem becomes computationally infeasible, as the set over which we are carrying out our search grows exponentially with the dimensionality of this vector S. Therefore, what one could do in order to tackle this problem, which is challenging, especially when the dimensions are large, is to utilize projected gradient descent. Projected gradient descent means that we're looking at this problem here, only the minimization of the distance, And this one can be tackled using gradient descent, which is given just here. Okay, so here we're taking, like at each step, we're taking our current estimate, we're reducing from it the gradient with respect to the symbols times the step size. Here eta t is the step size, and this pi here represents the projection, because these values of st cannot take any arbitrary value. They have to be in the set of plus minus 1 to take discrete values. So this is why we need this projection operator. And by taking the gradient explicitly, we obtain this expression here. And this is exactly the projected gradient descent algorithm for solving this problem here. Now, how do you unfold it? Let us look again at this expression. And as we can see, there's the expression here in blue, which is the conventional gradient descent, and the expression in red, which is the projection. And then we can replace each one of those with a dedicated layer which imitates this approach. So there's the operation in blue is exactly what we see here. This looks like the each step of gradient descent, in which instead of having a step size, we have those parameters delta, which are learned. And we're just taking this operation, which looks like gradient descent, and we're applying some conventional layer of a neural network to it. It's just some affine transformation followed by ReLU activation. So this value here, z of t, is exactly as if we taken our previous estimate and apply gradient descent and some layer of a neural network to it. And then this projection, which since we're projecting it to either plus or minus 1, but we want to be able to propagate to it, so we're taking some soft approximation of this hard projection, and it can be replaced with a sigmoid function, where a sigmoid resembles the projection into plus minus 1, it resembles a sine function. But instead of applying it just to this output, we're also adding another linear layer here in the middle. So we can look at it as if each one of those pairs is one iteration. It consists of two layers of a neural network. One, which is the layer here in blue, which is supposed to imitate the gradient descent step, and the layer here in red supposed to learn to carry out the projection step. And by doing adding a sufficient number of layers, we're actually obtaining a neural network, a deep neural network, in which the input to the overall network is y, the observation. The input of each layer to the t layer is this previous estimate of the previous estimate from the last iteration, and its output is the current estimate. And as we can see, there's like some sort of skip connections because the input was also provided to each one of those layers. And we also need to know the channel, which appears here. And by doing that, well, first, we have utilized knowledge of the channel. We end up with a relatively large network. What they have done in their paper, they train it with using about 250 million samples, where the largest channel condition they were tackling is the one, if I recall correctly, it had 60 different transmitters, which is a very large channel, very large, very combinatorically difficult task. Now, again, we're boiling down to the problem here that we end up with a very large network, a very large number of parameters to train. And although those parameters are inspired by an optimization algorithm, we do need a very large training set to train it. And we are, if the channel starts changing, we'll need probably to retrain the whole network. Also, specifically here for that net, we actually need to know the channel. We need to know its model and its parameters. So in the end of the day, the main benefit here over conventional algorithms, like actually implementing projected gradient descent, is mostly in inference speed. Namely, we don't have to actually carry out all those iterations. Doing it over a deep network is much faster than just doing the iterative process analytically. But on the other hand, we do need to waste a good deal of time and a good deal of computations in training this network. Now let us go to data-driven hybrid algorithms, in which the rationale is somewhat different compared to our previous approaches, which just used a deep network, either a conventional architecture or an unfolded one to carry out the complete symbol detection task. Here, the rationale is to select a symbol detection algorithm which is suitable for this specific channel and the specific problem, and to identify which of its computation requires knowledge of the underlying model. Then we replace those computations with dedicated and relatively compact networks, and we don't train the whole thing in an end-to-end manner. We're just training those dedicated components such that we can implement the overall algorithm in a data-driven fashion. As a first example of a data-driven hybrid algorithm, we shall consider the Viterbi algorithm. Viterbi algorithm is one of the main symbol detection algorithms. It's a fundamental tool in digital communication, and it can be considered to implement the maximum likelihood sequence detector for channels obeying this Markovian structure, in which the conditional distribution of the block of channel output given the block of inputs can be decomposed into the conditional distribution of each channel output given a set of L previous channel input. So it's exactly a finite memory channel, just like we considered for the sliding bidirectional recursive neural network case. And what Viterbi proposed to do in his algorithm proposed in the late 60s is to model each set of symbols which could have led to a single channel output as a state in a state machine, and then essentially do dynamic programming over it, which we will elaborate on next. This obviously worked very well. Viterbi ended up co-founding Qualcomm. Here is receiving the Medal of Science from George W. Bush. And to understand how this algorithm works, let us do it in a heuristic graphical manner, which captures the essence of Viterbi algorithm. So we have a finite memory channel. Namely, we have a channel in which the channel input at each given time only depends on its L channel input, on its L transmitted symbols. And in this specific example, we'll consider just memory of size 2, namely each channel output depends only on the current channel input and the previous one. And we're essentially building upon the fact that because it's a Markovian conditional distribution, we can factorize the log likelihood as the sum of corresponding log likelihoods. And then what we essentially do is, instead of computing this quantity here, we compute the quantity on the right using dynamic programming. And what does it look like? Let's say we have this channel output now, denoted Y1. We take this channel output and we're computing the log likelihood, the negative log likelihood, for each possible symbol combination which could have led to this corresponding channel output. And we're adding this to this graphical form. And here we're computing these costs for each specific combination of channel inputs which could have led to that specific channel output. And then the next thing we do is we update this path along this resulting diagram, which is what's called the trellis diagram. Then we take the second channel output. We again compute the log likelihood for each possible state combination which could have led to that. And then again, we're continuing by maintaining those overall paths where we sum the log likelihoods along each path. Again, another channel output comes in. We're again computing the costs, but then at some point we would start having conflicts, and we'd start having several paths leading to the same state. And what we do here, we only maintain the minimal path, the path with the minimal loss along it, which essentially boils down to dynamic programming. And once we do that, at some point we would have a state for a given time instance, only a single state has a legitimate path leading to it. And then we can use this specific state for decoding. Then we can actually know what was the symbol which was transmitted, in this case, 2 time instances after each symbol we're receiving. So this is why it operates in pseudo real time, namely it has some delay, which is dictated by the memory of the channel. And we do this all over again and again. This is actually how it operates. And what we see here is that, well, there are 2 things that happen. First, due to the optimality principle of dynamic programming, we're actually able to compute the negative log likelihood here to minimize it, which means that we're essentially implementing the maximum likelihood sequence detection. And since on each channel input we're computing the exact same number of log likelihoods, the complexity only grows linear with the block size. And we're so that it operates on pseudo real time, namely there's only a small delay here. Let us now observe the Viterbi algorithm and take a high-level perspective of it, and note that the only part of the Viterbi algorithm which requires prior knowledge of the underlying channel, namely the conditional distribution of the channel output given its input, is in the likelihood computation. Once we compute the likelihoods, the rest of Viterbi processing, which accounts for the temporal correlation for the finite memory of the channel, is essentially dynamic programming. It's just a set of algebraic manipulations. This allows us to implement Viterbi algorithm in a data-driven manner by simply learning to compute the log likelihoods. Here, which is what we call ViterbiNet, we replace the likelihood computation, which are model-based, with learned likelihood computations. And once we do that, assuming that we have an accurate estimate of those likelihoods, we can actually implement Viterbi algorithm in a data-driven fashion by learning only what has to be needed for Viterbi. Now, we note that, for example, if the channel is stationary, then this mapping of the channel input into a set of log likelihood values does not depend on the time index. There's only one function which has to be learned. So how do we learn it? Well, there are actually two different approaches to do that. First is to use classification networks. Namely, we first use a classification network to compute the conditional distribution of the symbols of the channel input given the observed channel output, and then we convert them to the desired quantity, which is the conditional distribution of the output given the set of inputs which could have led to that, where the Markovian structure of the channel is encapsulated. It can be inferred from the previous quantity using Bayes' theorem. Alternatively, we can also use regression networks. Namely, we can assume some given conditional distribution of the input given the set of the channel output given the set of channel inputs, which is what we're interested. We can assume that it is only dictated by its first and second order statistical moments and only estimate them. So how do those architectures look like? Well, for the classification network, let's know that it consists of two components. The first component is this classification network whose input is the channel output, and its task is to recover the set of channel inputs, the set of symbols which could have led to this channel output. Now, since it's a classification network, it's trained to minimize the cross entropy loss. It has a softmax output layer. Then essentially what we learn here is the conditional distribution of each possible pair, of each possible combination of channel inputs given that channel output. And now let us recall that classification networks are capable of accurately learning the conditional distribution of a cat given an image, which is way more complicated than learning the conditional distribution of a set of constellation symbols given an observed channel output. So this implies that we can use a relatively compact network here in order to implement this part. However, what we are interested in is not the conditional distribution of the channel inputs given the channel output, but the opposite. So what we can do is use another machine learning tool to learn the marginal PDF, the marginal probability density function of the channel output. And we can build upon the fact that, for example, we know that the input is discrete, so the marginal distribution of y has to obey some finite mixture model. And so we can use some sort of kernel density estimation, like a finite mixture model PDF estimator, to estimate it reliably using, for example, some expectation optimization algorithm, and then combine those two quantities using Bayes' rule to obtain a hopefully accurate parametric estimate of the channel output, the conditional distribution of the channel output given each possible combination of channel inputs which could have led to that, which is exactly the quantity we need for Viterbi algorithm. These are the values assigned to each one of those cost values along the trellis diagram. Alternatively, we can also use regression networks. Namely, here, our input to the network is the combination of channel inputs, namely the state. And the output are the estimated first and second order statistical moments of the channel output given those pairs. So this does not explicitly estimate the conditional distribution. It estimates the first and second order statistical moments of this conditional distribution. And then once we have these quantities, we can just estimate the conditional distribution as Gaussian. Now, the question is, how do you train a regression network to learn the mean and variance of conditional distribution? Well, there are two approaches to do that. The first is to minimize the objective, which can be treated as the negative log likelihood, assuming that it's a Gaussian conditional distribution. So this is exactly the negative log likelihood. It's one possible way to do it. Alternatively, we can just look at this mean value as an MSE estimate of the observation and the covariance matrix as an MSE estimate of the empirical covariance. Here, it's not the covariance, it's the empirical second order statistical moment, but these are two methods using which one can implement a regression network to learn the first and second order statistical moments of the conditional distribution of the channel output given a combination of channel inputs which could have led to that. Now, both approaches which we have discussed, the one uses classification and the one uses regression networks, provide a parametric estimate of the conditional distribution of the channel output given each possible set of channel inputs. Using that, we can implement Viterbi in a data-driven manner. And does it work? Well, let us see for this numerical example here. Now, here we're considering a network which is trained with merely 5,000 symbols. Let us recall that the previous examples we discussed were trained using the orders of several millions of training symbols. And what we have here, the curve in blue, is the performance of the Viterbi algorithm, which knows the channel at each given time instance. And the curve in red is the performance of ViterbiNet. And as you can see, it essentially coincides with Viterbi algorithm when trained using a very, very small number of training symbols. Now, we can also see that the curve here in purple, this is the SBRNN receiver we discussed earlier, through the trained using the same number of training samples. So as you can see, the performance gap is not that big, but still, the ViterbiNet algorithm actually approaches the performance of its model-based counterpart since it is designed to do so. Now, another advantage of going into machine learning-based methods is that you obtain improved robustness to uncertainty. What do we mean by that? Now, if we implement model-based Viterbi, but we do not know the channel exactly, we have some error, then the performance deteriorates significantly. This is the black curve here. Now, also the SBRNN, if it's trained on a set of channels, each one with slightly different statistical characteristics, meaning that we did not know in advance to exactly which channel we will be tested in during inference, then the performance significantly deteriorates when we're using a relatively small number of training symbols. However, the green curve here, this is ViterbiNet trained using the same level of uncertainty, namely over a variety of different channel conditions. And as we can see, it actually obtains a performance which is very close to as if it was trained using the exact same channel conditions over which it is tested. Namely, by using machine learning tools, embedding it into a symbol detection algorithms, we're able to robustify it. We're not only able to approach its optimal performance, namely we're approaching a maximum likelihood sequence detection using a relatively small number of training sets, we're also improving robustness to uncertainty. Now let us proceed to another form of symbol detection based on graphical models. And if we started with Viterbi algorithm, let us continue to what's called factor graph methods. Now, a factor graph methods are a family of signal processing algorithms which are based on the ability to represent distribution at a graph, and then they carry out inference using message passing over the graph, exploiting the graphical model to implement this with reduced complexity. Okay, so this sounds like very high level, but let's understand how does this work. Okay, so to that aim, let's go back to our finite memory channel, in which the conditional distribution of a block of channel outputs given its corresponding channel inputs can be factorized using this Markovian structure. Okay, so what we do here, we define a state vector, which is a set of channel inputs which could have led to the, which are statistically related with the given channel output, the given observation. And then we can write the joint distribution of this block of channel output and the block of channel input using this factorization. And what we do, we call this function here the function node, and the variables inside it we call the variable edges, and then we obtain this graphical representation which encapsulates the joint distribution of the channel output and the channel input. Now, this graphical representation allows us to carry out inference with relatively low complexity. And in order to do that, we will go into what's called the sum product algorithm, or specifically its special case for these kinds of joint distribution, which is what's called the BCJR algorithm. So in order to do that, let's understand how can this graphical model facilitate the computation of marginal distributions. Let us look at the marginal distribution, marginal joint distribution of the channel output and two consecutive states. Now we know that this joint distribution using the law of total probability can be obtained by summing over the overall joint distribution. Now let us write this overall joint distribution using its factorization, where these are the function nodes and these are the variable edges. And then we can actually write this as the function node which is relevant to the current two states which we are observing, as well as this term here, which we will call the forward message, as well as this term here, which we will call the backward message. And actually, we've managed to factorize this this marginal distribution into a product of three components, in which the forward message can be actually computed recursively, because we can write it down explicitly, and again, exploit this Markovian structure to see that it can also be obtained directly from the forward message with respect to the previous state. Now, the same goes for the backward message. Now, this term here can also be factorized as follows, and we can also obtain it in a recursive manner from the backward message of the next state. So, if we now look over the factor graph, this graphical representation of the joint distribution, we can actually see that if we want to compute the marginal distribution of states S3 and S2, as well as the overall observed block of channel output, all we need are the backward messages along the graph to here, the forward messages along the graph here, where each can be computed recursively, and the value of the function node here. Now, by computing this marginal distribution, we can actually implement what's called the BCJR algorithm, proposed back in '74, which first computes those marginals by message passing over the factor graph, which is what we just explained, and then use them to compute the maximum posteriori probability by simply doing maximization with respect to the specific state, which we are, with respect to a specific symbol, which we are interested in. So what this computation allows us to do, it allows us to compute this marginal distribution in a linear complexity due to its recursive manner. And then we can use this quantity to evaluate the maximum posterior probability symbol detector for each given symbol. Namely, we're actually implementing here the optimal symbol detector in the sense of minimal error rate. Okay, so this is the BCJR algorithm. Now let us note that all we needed in order to carry it out was knowledge of the factor graph. So if we were to know the factor graph, namely we were to know the function nodes, we could have carried out the message passing over the learned graph. So what we are proposed to do here, what we call BCJRNet, is essentially to learn the factor graph and then do message passing over the learned graph. This is based on our previous knowledge that the channel obeys this Markovian structure. Once we know that, all we have to do is learn those function nodes. And once they are learned, we know the graph. Now, how do you learn them? Okay, so let us note that for a finite memory channel, those function nodes, which are what we are interested in, can be written as the product of the conditional distribution of the channel output given its corresponding state times the conditional distribution of the corresponding state given the previous state. That just follows from the Markovian structure. Now, we know that this term here is typically known, right? Because it's the conditional distribution that a set of symbols were transmitted given the previous set of symbols. So it usually obeys some sort of a uniform distribution if one is a shifted version of the other. So this can assume to be known. It typically is known. The other quantity, which is unknown, which actually depends on the channel, you can note that it is exactly the same quantity which we learned in the turbinate. which means that we can learn those function nodes using the same architecture we used for Viterbinet. And again, if the channel is stationary, it means that those function nodes are exactly the same function throughout the complete block. So we only need to learn one function node. We only need to train one of those neural networks to learn this conditional distribution and combine it with our knowledge of the condition of the transition distribution and our knowledge of how the BCJR algorithm operates over the factor graph, where instead of using the model-based factor graph, we're using the one which we learn. And that is what we call BCJRNet. We're applying BCJR of the learned graph. And assuming we have an accurate estimate of the function nodes, we actually implement map symbol detection. This actually was just recently published in our ISIT. It is also available on arXiv, this paper. So how does it work? Well, actually, by doing so, we don't need a lot of training symbols here. Notice these are 10K symbols. Again, please recall that for previously proposed deep detectors, one had to use the order of 10 million, 100 million training samples. Here, we're talking about 10,000 training samples. And by doing so, we're actually able to implement the BCJR algorithm. So the red curve, which we don't really see, is the data-driven BCJR algorithm, and the blue curve is the learned one. So we are actually able to learn the factor graph accurately and obtain the exact map maximum posteriori probability symbol detection as the model-based BCJR. Again, we also see that by utilizing machine learning, we're improving robustness to uncertainty. Because if we have some level of uncertainty in our knowledge of the channel, we get inaccurate function nodes in the factor graph, and the model-based BCJR algorithm deteriorates. However, under the same level of uncertainty, the data-driven implementation, namely when it is trained over a variety of channels, because we do not know in advance exactly to which channel it is applied, but it's in the same order of uncertainty as the order of under which we have tested the BCJR algorithm here, we're actually able to learn the function nodes quite accurately and obtain roughly the same performance as if we had trained the function nodes over the exact same channel conditions under which it is tested. So we're actually here able to learn optimal symbol detection. We're able to learn the maximum posteriori probability symbol detection from data by learning the factor graph and building upon this learned factor graph to implement the algorithm which we know is suitable for such channels, which is the BCJR algorithm. Before we go further, let us do some brief comparison between Viterbi and BCJR, which are the two algorithms we've considered as symbol detection over finite memory channels. Now let us recall that first, what Viterbi does, it computes the maximum likelihood sequence detector, while the BCJR learns the map symbol detector. So the BCJR actually minimizes the error rate for each given symbol. Now, the complexity of both algorithms grows linearly with the block length, but it does grow exponentially whereas the number of states or the channel memory or the cardinality of the channel inputs, the constellation size. So once these grow large, either the cardinality of the input or the memory, both algorithms will become very computationally complex, but it should be noted that typically BCJR is more computationally complex than Viterbi, even though they both grow linearly with the block length. BCJR requires those two-directional recursion, while Viterbi only implements a one-directional recursion, only the forward path. Viterbi, due to the fact that it only computes the forward path, is able to operate in real time with some delay, which is dictated by the memory, while BCJR requires the complete block to be received before it can detect it. And both give rise to data-driven implementation. One is Viterbinet, and the other is BCJRNet, which utilize relatively small training set in order to learn to carry out those model-based algorithms. So far, we have considered the application of data-driven hybrid algorithms for the family of finite memory channels. This was done by identifying the proper symbol detection algorithms, either the Viterbi algorithm or the BCJR algorithm, and replacing their model-based computations with dedicated machine learning methods. By doing so, we ended up with a data-driven implementation of the model-based algorithm. Let us now proceed to a different family of channels, to MIMO channels without memory. Here, the cardinality of the measurements, which is dictated by the number of antennas, can be very large. Also, the cardinality of the input, which is dictated by the number of transmitters, can also be very large. As a result, the algorithms we've considered earlier, the BCGR algorithm, the Viterbi algorithm, are simply not feasible here, regardless of whether they're implemented in a data-driven fashion or in a model-based fashion, because the complexity grows exponential with the cardinality of the input. This gives rise to the question, which symbol detection algorithm one should use and can be implemented in a data-driven fashion for MIMO detection. To that aim, let us look at two extreme cases, which are separate decoding and joint decoding. Joint decoding is the optimal approach. It means that we're taking the channel output and we're simultaneously trying to recover the combination of channel inputs which could have led to that specific channel output. For example, if we look at a linear channel with Gaussian noise, like we did in the derivation of DetNet earlier, the resulting problem boils down to this optimization, which is carried out over a set whose cardinality grows exponentially with the number of transmitters. Hence, it becomes unbearably complex when the number of users is very large. Alternatively, the dominant approach currently in the massive MIMO literature is to implement separate decoding. Separate decoding means that we're using the channel output to decode the symbol of each user separately while treating the remaining symbols as noise. For example, if we go again to a linear MIMO channel, a Gaussian channel, this can be carried out by taking the channel output, applying some linear filter to it, and trying to recover the corresponding symbol from the output of that linear filter. As a result, the complexity here only grows linearly with the number of users. However, its performance is strictly suboptimal, and in one of our recent works, we actually characterized how suboptimal is separate decoding in the massive MIMO regime. There is another approach which combines separate and joint decoding, and this is the family of interference cancellation methods. Interference cancellation methods decode the symbol of each user separately. However, in each such decoding, previous decoding of the remaining symbols, namely the interference, is used to facilitate the recovery. By doing so, operating in such an iterative fashion, one can obtain some balance between performance, approach the performance of joint decoding, and complexity, namely maintain a complexity which only grows linearly with the number of transmitters, like in separate decoding. Specifically, the iterative interference cancellation method is based on implementing separate decoding multiple times while utilizing the decoded symbols in the previous iteration to facilitate recovery in the current iteration. There's also the problem here of error propagation, and if we have decoded one symbol incorrectly, it may influence our ability to recover the remaining symbols, and that motivated the derivation of a soft interference cancellation method. Was derived about 20 years ago, and here, instead of estimating the symbols in each iteration, we're estimating a conditional distribution, which to facilitate the estimation of the remaining symbols in the next iteration. So this looks like the block diagram we have here. We have the channel output. We're doing interference cancellation and recovering an estimate of the soft symbol at each iteration. And then we're using those soft symbols to cancel the interference in the subsequent iterations. Going into further details, the soft iterative interference cancellation algorithm considers the symbol detection over linear Gaussian MIMO channels of the following form, in which the channel vectors denoted H1 to Hk are known. And then it operates in an iterative fashion, where on each iteration index Q, it implements a mechanism for canceling the interference and estimating distribution of each symbol of index K using the channel output and the estimated interference from the previous iterations. In particular, the interference cancellation block, marked here, takes the channel output, provides an estimate of the interference using the mean values, and then just cancel the interference by subtraction, as we see in this expression here. And furthermore, the conditional distribution estimates from the previous iterations are also used to provide an estimate of the soft symbols. How is that done? We're taking the interference canceled channel output, and we're assuming that its distribution, given the current symbol, obeys a Gaussian distribution with some mean value, which is dictated by the current symbol and the channel vector, but also the variance here is determined by the variance of the noise plus the estimated variance of the remaining symbols computed from this conditional distribution estimate. By doing that, we essentially model the interference as noise with a known variance and mean. By doing so, we can now obtain an estimate of the conditional distribution of the desired symbol given the interference cancelled output from this Gaussian distribution via Bayes' theorem. The soft iterative interference cancellation detector depicted here is highly model dependent. Its model dependence is reflected in several parts of the algorithm. First, it assumes a simplified channel model in which the interference can be cancelled by subtraction. Namely, the channel has to be linear, in which the effect of the interference is additive. Furthermore, the channel noise has to be Gaussian. Not only Gaussian, it has to be white Gaussian. And the channel parameters, namely the channel vectors, must be accurately known as they are repeatedly used throughout the algorithm. Now, if you have some uncertainty, the performance is expected to deteriorate, motivating us to look into channel model independent implementation, a data-driven implementation of soft iterative interference cancellation by integrating machine learning methods. This work, which is called DeepSeek, is actually presented later on this week here in Icassp, and it begins by considering the soft iterative interference cancellation detector, identifying its basic building blocks, which operate on the postulated conditional distribution of the interference and the channel output, and they produce an estimate of the distribution of the corresponding symbol. As such, each one of those building blocks essentially implements a classification task in which it outputs a conditional distribution of a label, which here is the symbol, given its input. Consequently, such building blocks can be accurately learned using classification network with softmax output layer trained to minimize the cross entropy objective. Consequently, we can implement soft iterative interference cancellation method in a data-driven manner by replacing those building blocks with dedicated classification DNNs. Now, the question that comes to mind is, how do you train the resulting architecture? And there are actually two approaches to train this resulting architecture. First, it's just train the whole thing in an end-to-end manner. Namely, we take the sum cross entropy loss, which means that we're essentially only looking at the overall output of the deep receiver. Now, by taking this approach, we're essentially using our training to jointly adapt all the parameters of the system, indicating that we are expected to need a large number of labeled samples in order to train the network. Alternatively, we could also build upon our prior knowledge of the purpose of each one of those building blocks, and we can train each one sequentially using the blockwise cross entropy loss. Here, we're using the same training set to adapt each one of those building blocks separately. Namely, this training set is used to adapt a much smaller number of parameters, implying that the overall receiver can be trained using a smaller number of training data. Here we'll only show one numerical example. I invite you guys to attend our talk later on this week, in which we'll present a more in-depth analysis of this architecture. But what we see here, well, this is just a small scale channel, a 6x6 Gaussian channel, for which we can actually compute the minimal achievable error. This is the red curve. And the blue curve is the performance achievable using the model-based iterative soft interference cancellation method. Now, the purple curve and the green curve here are the performance achievable using the proposed architecture, whether it's trained in an end-to-end manner or trained sequentially. Now, as we can see, the performance comes quite close and even essentially coincides with the model-based algorithm, which, as we can see here, achieves relatively good performance, which is quite comparable to the minimal achievable error rate. For comparison, this is DetNet, the unfolding based, which is trained here using 100 times more samples compared to the ones we use for training DeepSeek. The performance it achieves here, this very poor performance, is what happens when it is trained using the exact same number of training sets. Furthermore, we again see that not only are we able to learn to implement interference cancellation from a small number of trainings, from a small training set, we also obtain improved robustness to uncertainty. Again, we can plot here the curves. The dashed curves are the same model-based algorithms, but here they have inaccurate knowledge of the underlying channel. As we can see, they deteriorate significantly. For comparison, our algorithm at the DeepSeek, both with end-to-end training and with sequential training, achieves roughly the same performance as it does with accurate training, implying that by implementing the algorithm in a data-driven fashion, we're not able only to operate without prior model knowledge, we're also improving the robustness to uncertainty. Now, again, I invite you to join our presentation of this work later on this week, in which I will also show how it operates in much larger scale channels and for nonlinear channels. So far, we have developed hybrid data-driven algorithms for symbol detection, namely Viterbinet, BCG-RNet, and DeepSeek. One of their main advantages is their ability to adapt using a relatively small number of labeled samples. What we're going to show now is how this ability can be translated into the capability of tracking channels in an online manner. To that aim, we will exploit the inherent structure of digital communications, recalling that in digital communication, the bits are not purely random. For example, protocols induce structure. They imply that if we have a message conveyed from a transmitter to a receiver, what is actually transmitted over the channel is not just the message, but also header and pilots, which imply that there's a small portion of the frame which is known to the receiver and can be utilized to adapt its deep symbol detector, assuming that this deep symbol detector can be tuned using a relatively small number of training samples. Furthermore, the presence of error correction codes can only so be exploited. Error correction codes implies that if we transmit a message from a transmitter to a receiver, even if the symbols are improperly detected by the receiver, it may still be able to recover the message by utilizing the presence of error correction codes. How can error correction codes be exploited to facilitate online training? Well, what we're going to show here is that the presence of these error correction codes gives rise to semi-supervised training. To that aim, let us consider a coded communication setup as depicted here. Here, the transmitted bits are first encoded using a forward error correction code and modulated into a set of symbols transmitted over the channel. They are recovered using some pre-trained deep symbol detector into a set of symbols, which are then forwarded to decoding using a forward error correction decoder. Now, the channel may start changing in time such that at some point, we may start observing errors due to the fact that the channel with which we were trained is no longer the channel under which we are operating. So we may have some symbol detection errors. However, if the number of errors is not larger than the homing distance of the code, we should still be able to recover the bits accurately. And if we have an accurate recovery of the bits, we can re-encode them and remodulate them, generating our knowledge of what the transmitted symbols were, allowing to adapt the deep symbol detector using our knowledge of the channel output and our encoded and modulated symbols as to train in a self-supervised manner. Consequently, we are now able to track channel variations online by utilizing data combined with our prior knowledge of the inherent structure induced by error correction code to train our deep symbol detector to track channel variations online without having to provide additional artificial training. Now we will show a numerical example demonstrating how this works. We will transmit a set of Reed-Solomon block code words. Each code word corresponds to a single block, and the channel changes between blocks. Now the block size here, this is a 255 on 2 to 3 Reed-Solomon block, means that each block corresponds to the order of only 2,000 symbols. Now, we will compare here the performance of Viterbinet with online training, the proposed approach, and also to Viterbinet, which is only trained once using the initial channel condition, and Viterbinet only trained once, but using a broad set of channels. This is what we call composite training. And we will compare it to Viterbi, which operates with instantaneous channel knowledge, know the channel knowledge at each block, and Viterbi, which only knows the first channel. So let us begin. And what we are going to see here in this upper plot, this is the bit error rate of all those detectors per block. And in the lower plot, we see these are the taps of the channel and how they change. And as we can see, the taps start changing in time, and at some point they become notably different from the initial channel taps, and then we start seeing errors in the initially trained and in Viterbi with only initial channel state information. At some point, we can see that the channel is much more attenuated compared to the initial channel, and then we start seeing errors appearing, but still we are able to track the channel online using ViturbiNet. At some point, even ViturbiNet with online training exhibits some errors, but it is still capable of tracking the channel variations online, maintaining negligible bit error rate over time. And at some point, this is a periodic channel. It will return to its initial state. And then what we can see is that ViturbiNet with online training is actually able to track it all the way. Now, this is an experiment which is carried out on a laptop, on a conventional laptop. So the fact that ViturbiNet can train with a very small number of training set allows us to actually implement this in real time, because not only can we adapt using a very small number of training samples, also this training period is relatively small. To conclude this part of the talk, we emphasize that wireless communication is inherently different from conventional machine learning applications like computer vision and speech processing. First, there are established algorithms to tackle these problems, at least those of receiver designs which we are considered here, such that optimality is achievable and actually matters. Namely, if we have a receiver which operates well on a broad range of channels, doesn't mean that it is optimal for any. Furthermore, channel conditions are dynamic, and we want to be able to track those variations online, motivating the need to first utilize architectures which do not require a large number of training samples, and the ability to exploit the inherent structure of digital communications. Now, we know that machine learning brings powerful data-driven tools which can facilitate and improve existing wireless communication algorithms. Yet, machine learning is not magic. In the end of the day, it's highly parameterized optimization, which typically requires large label dataset. As Yoda says, use it wisely. Not just plug and play, we need to understand how to use it and how to combine it with existing knowledge, taking into account its capabilities and its limitations. What we have showed here and focused this part of the tutorial on is on data-driven hybrid algorithms, which are able of improving existing communication algorithm by allowing them to operate in a data-driven fashion, such that we remove their model dependence. For example, we can now implement iterative soft interference cancellation without being restricted to linear channels. And it also robustifies these algorithms, reducing their sensitivity to uncertainty. We also shown how by exploiting the structure of digital communications like protocols and channel coding, one can train deep receivers to track channel variations in an online manner in a semi-supervised fashion without having to provide additional synthetic training. So far, we've just discussed symbol detection. There are many other areas in signal processing which are dominated by model-based algorithms, not only symbol detection in communications. Well, there are other aspects on communications, but also in radar and control and various other signal processing applications. And we conjecture that the approach of hybrid data-driven algorithms can have great potential beyond wireless communications. And essentially what we showed here, we believe, is only the tip of the iceberg in combining machine learning and model-based algorithms. The application of machine learning, and particularly of data-driven hybrid algorithms for wireless communications, gives rise to a multitude of interesting research directions. To name a few, we first note that empirically, those data-driven hybrid receivers such as ViturbiNet and BCJ-RNet and DeepSeek were able to achieve their performance of their model-based counterpart for a broad range of channels using the exact same architecture, where the difference was in the samples used for training. This indicates that perhaps by utilizing machine learning, one can implement a feasible and hopefully also provable universal detector, namely a detector which is capable of achieving performance within a controllable gap from the optimal performance over a broad range of different statistical channels. Additional issues for future research are more from an applied perspective. For example, one can consider the optimization of deep receivers, like utilizing additional forms of structure inherent to coded communication, to digital communications, like frame and packet structure for online adaptation, utilizing model learning to determine the architecture, the number of layers, the number of hidden nodes in each layer to optimize the performance of deep receivers. Additional use cases can be considered. We have looked at a receiver design for finite memory channels and for uplink MIMO channels. For downlink MIMO channels, for example, we know that successive interference cancellation combined with superposition coding can approach the capacity region of downlink NOMA systems, motivating looking into the implementation of these model-based algorithms in data-driven fashion. Finally, we can also note that the weaknesses of deep learning can have an effect on their implementation and application in wireless communication. For example, we know that deep networks are sensitive to adversarial examples. Namely, one can provide an input with a very weak level of noise, which will change the inference and decision of those deep networks considerably. This gives rise to the potential of new jamming methods designed for deep receivers, aiming to exploit their weaknesses to adversarial examples. Consequently, the combination of machine learning and wireless communication gives rise to a multitude of exciting new research directions, and we hope we have given you some pointers and intrigued you for your future research.
Hello, everyone. I'm Vince Poor, and I'm the third member of this tutorial team. As Yonina said at the beginning, there are really two parts to the connection between machine learning and wireless communications. One is using machine learning to optimize wireless communication networks. And this is the aspect that Yonina and Nir have been talking about so far. The other side of the coin is the use of wireless communication networks as platforms for machine learning. And that's what this third part of the tutorial is about, and what the remaining part of the tutorial is going to be addressing. So I'm going to talk about basically two things in this context. One is so-called federated learning, which I'll explain a bit more in a minute. And the other is decentralized learning, which I'll also talk about later. I'm going to share this part of the presentation with Nir. So the way it's going to go is I'll first talk about some basic things about federated learning. Then Nir is going to talk about uplink compression for federated learning. And then I'll come back at the end and talk about decentralized learning and then wrap up the tutorial. So why don't we get started? So first of all, just take a step back and look at the so-called state of the art, I guess, in machine learning. This is greatly oversimplified, but just to set the stage a bit. So first of all, why has machine learning been such a big thing in recent years? Well, it's not a new technology. Of course, machine learning goes back quite a ways, decades. But lately, in more recent times, we see more and more data being available, both because of the prevalence of personal devices and also because of the internet. And there's been a significant increase in computational power to deal with that data. So this means it's been possible to apply machine learning in a great number of areas. So standard machine learning, and I put standard in quotes because of course it's just an oversimplification, but basically standard machine learning is implemented in a centralized manner, that is in a data center or in the cloud. And the learning algorithm has full access to the data. On the other hand, and at the same time, there are also state-of-the-art models, such as deep neural networks, that can be applied in this way. And these are managed and operated by standard software tools like TensorFlow and specialized hardware. On the other hand, there are applications where centralized machine learning might not be the best choice. So examples include autonomous driving or self-driving cars, first responder networks, tactical networks, and others. And what makes these applications different are several features. First of all, the data is at the edge. It's born at the edge of the network, either on iPhones or IoT devices, so it's already there. If you're in a wireless situation, which of course all of these are, there's limited capacity to upload data to the cloud. So immediately you see there's a problem. If you have a lot of data to be uploaded, there's going to be an issue. Secondly, in many of these applications, there's requirements for very low latency. So ultra low latency communications, particularly, for example, in autonomous driving. And if you have to upload data all the way back to the cloud, then that's going to add to the latency. Data privacy is another issue because if you keep the data at the end user devices, then its privacy is maintained. I'll say more about that later. And then also just the applications may involve the locality where the end user devices are. And so it's not necessary to think about loading data up from a broad network into the cloud in order to build models. So these kind of considerations motivate moving learning closer to the network edge. So I'm going to talk about here a couple of things, and I'll start with the machine learning, the standard machine learning paradigm I just discussed. You have data, which is collected, say, at the edge, uploaded into the cloud. The cloud builds models or a model and downloads that to the end user devices. So the computations are done all in the cloud. The end user devices can be just data collectors, and they don't need to be able to do any machine learning. In federated learning, the end user devices are themselves going to do the learning. So data will be collected at the end user devices. They will learn a common model independently, upload their model to say an edge device, which could be take the role of the cloud here. The edge device will serve as an aggregator. It will aggregate those models and send the aggregated model back to the edge device or to the end user devices, where it can be updated again, and there can be multiple iterations of this process. And then finally, a decentralized machine learning is a different model where, again, learning is done by end user devices, but then there's no device playing the role of the cloud. That is, all the learning is going to be done on the end user devices. There's no aggregator, but there may be peer-to-peer communications where there can be some consensus achieved about what models should be. So here I'm going to talk about federated learning, and I'm going to talk about decentralized learning. So start with federated learning. What are some challenges? Well, one is just the communication bottleneck. As I said, we're talking about a wireless network. Data has to be uploaded even from the end user devices to an edge device or an access point. So there's going to be a bottleneck there. There are usually many end user devices for each edge or access point device. There's going to be statistical heterogeneity. That is, not every device is going to have the same quality of data. There's going to be system heterogeneity. Not every device is going to have the same capability for computation and so forth. Privacy and security, of course. Once you have a lot of devices in a wireless network, there are going to be possibility of intruders and all kinds of other things. And I'll talk about that a bit later as well. But communications and information theory can help tackle most of these challenges. So if we're going to look here mainly at the communication bottleneck. And in order to handle the communication load, there are going to be a couple things we have to look at. One is user selection. Another is compression and source coding. And then we have to worry about non-orthogonal transmissions, which are going to cause interference. And finally, over-the-air computations, which it means that we may be able to use the actual superposition property of the wireless medium in order to do some of the computations for us. So why don't we move ahead and talk about user selection and interference and how that interfaces or interplays, if you will, with federated learning. Okay, so here's another model, reminder of the model for federated learning. We have end user devices where learning is going to go on. Models are shared with an edge device or access point where it's aggregated and then returned back to the end user devices. Okay, so the basic idea of federated learning is we want to enable those end user devices to do machine learning without centralizing their data. Key features again, own device data set, so the end users keep raw data locally. On device training, the end user devices are powerful enough that they can train algorithms there on a shared model. Federated computation, they're going to send, the end user devices are going to send their models up to an aggregator, access point, if you will, or edge device, which is going to collect trained weights. So if we think about a neural network, for example, those are going to be aggregated in some way, perhaps averaged. And then that shared model is going to be sent back down to the end user devices where it can be, the process can be iterated. And in this situation, we're going to get privacy by default. And I really should put that in quotes because I'm going to say a bit more about that later. There are some issues there. But if you think about what this means basically that the actual raw data is not going to be transmitted anywhere. It's going to stay on the end user device. So here's the operation, if you will, of federated learning. We're going to iterate the following process until convergence. At the end user devices, we're going to perform local training. We're going to send trained weights to the aggregator. And then at the aggregator, the aggregator is going to average the model. So the aggregator is the access point and redistribute it to the devices. And again, we're going to iterate on that until we get some kind of convergence. Now, what are some issues that come up here? Well, because this is a wireless network, the communications from the end user devices to the edge device or access point needs to go through wireless channels. So the communication medium is shared and resource constrained because it's a wireless medium. So because it's resource constrained, only a limited number of devices can be selected in each update round. And because it's a shared medium, there's going to be interference. So the transmissions may not be reliable for that reason. So two questions that arise here that we're going to address in this part of the tutorial is how should we schedule devices to update the trained weights? And how does interference affect the training? So here's another way to think about federated learning evolving over time. First of all, there's the access point or the aggregator is going to select a certain number of end user devices for upload. Those devices can train and then send their trained weights to the aggregator. Some of those transmissions are going to be unsuccessful. And then we're going to iterate again. So there's going to be another round of the same thing, and we're just going to keep going until we converge. So the two kinds of things that can happen are, if you're an end user device, you're not selected, and so therefore you can't at that time send your updated weights to the aggregator, or you may be selected and yet you can't transmit because of some of the impairments of the wireless channel. Okay, so here's a system model that we're going to look at for this, so we can try to get some understanding of it. First of all, we have a mobile edge network, so we have access points and end user devices that are capable of computing. The access points we'll just assume are distributed in some kind of Poisson process. And each access point is going to have K end user devices associated with it. And then the spectrum is going to be divided into N subchannels, where N, of course, is less than K. And that spectrum is going to be globally reused from access point to access point. Okay, so one of the first questions we're going to have to ask is how to schedule these users. But first of all, let's just look at the federated learning again. Again, there's own device training. And what's going to happen is each end user device is going to train a statistical model using its own data. The end user devices are going to download a shared model from their access point and perform local computing. Then each access point is going to select N of its K end user devices to update the trained parameters at a given iteration. And then each access point is going to update its model and redistribute it to its end user devices. So this is going to be going on in multiple cells with multiple access points. So now the first question we might ask is, how can we schedule the access points to schedule the end user devices to upload their data on each round. And to look at that question, I'm going to look at 3 standard scheduling mechanisms, and the idea here is you want to compare their performance in federated learning setting. The first one is random scheduling, where the access point uniformly selects n, remember n is the number of channels, out of its k end user devices at random. So random scheduling. The second scheduling mechanism is round robin, where we just divide the end user devices up into G groups, where G is determined by the number of end user devices and the number of channels, and is just going to sequentially select those groups as the model is updated iteratively. And finally, there's proportional fair scheduling, where the access point is going to select n of the k end user devices with the strongest signal to noise ratios. Okay, so it's another technique. Now, what I'm going to talk about now is an analysis that appears in the paper that's shown here at the bottom of this screen, which appeared just a few months ago in the IEEE Transactions on Communications. Okay, so now we have these scheduling mechanisms. We're going to be transmitting over a wireless network. So a trained update can be successfully received by the access point if and only if 2 things happen. First of all, the end user device for that particular model has to be selected by the access point, and even if it's selected, the received signal to interference plus noise ratio at the access point has to exceed a decoding threshold, which we'll call theta. So theta is a parameter of this model, which will come up later. So this gamma sub kt is just the SINR at the received at the access point for the kth end user device at iteration t. And a metric to quantify the effectiveness of training is going to be the number of communication rounds required to reach an epsilon accurate solution. And by that I mean, so here we're going to be solving a very tame machine learning problem, and just to look at the communications aspects. In particular, we're going to be looking at minimization of a strongly convex function. So in this case, you know you're at a minimum when the primal and dual solutions agree. And an epsilon accurate solution is one where the difference between the primal and the dual solutions is less than or equal to epsilon. So when epsilon is small, you're getting to a very close to optimum. Okay, so that's what we mean by an epsilon accurate solution, and epsilon is going to be another parameter in this model. Okay, so in this setting, with some assumptions that are found in that paper, I won't go through them all in detail here, we can actually get lower bounds on the number of communication rounds, and they're given here in these formulas. I'll give some approximations in just a minute, but the parameters are, as we've seen, there's theta, which is the threshold for decoding. There's epsilon, which is the quality of the solution. And there are 3 more parameters, which I didn't mention yet. One is the path loss exponent alpha. Another is the precision level at the end user devices of machine learning. So we're going to abstract the machine learning at the end user devices into a precision level that can be achieved there. And N is just the total number of exemplars distributed over all of the end user devices. So don't worry too much about these formulas. I'm going to give some plots in a minute. But we can also do some approximation for special cases. If we have a high SINR threshold, which means basically a lower quality code, so this is a more challenging situation, we can approximate the 3 lower bounds in this way. For random scheduling, round robin, and proportional fair, basically what we can see with these approximations is that random selection, round robin have approximately the same behavior, whereas proportional fair actually has a lower bound. Okay, so these lower bounds are just lower bounds, but they're going to be proxies for the performance, and we'll see that they also do predict some performance in actual machine learning. On the right is an approximation when the theta, that is the SINR threshold for decoding, is small. This is a case where we have a really good code. We don't need a lot of SINR to decode. In that case, we see that random scheduling and proportional fair have the similar convergence performance, while round robin has better speed up. So for a good channel, round robin is better. For a bad channel, proportional fair is better, as you might expect. And here's a chart just to show that for a particular set of parameters. The left-hand side is for a high decoding threshold, 15 dB. The right hand is for a low decoding threshold, minus 25 dB. And you can see that in the left-hand side, the lower bound for proportional fair is much lower than the lower bound for the other two other two scheduling protocols, and that's just consistent with intuition, because if you have a poor channel, you need to pay more attention to the signal to noise ratios. On the other hand, on the right-hand side, where you have a really good link, then we don't really have to worry too much about that. We can just go round robin and still get good performance. So blue here, the lower one on the right is blue, which is round robin. On the left, green, which is proportional fair. We can also use these lower bounds to look at the issue of how we should divide up the spectrum, excuse me. Obviously, if we have larger subchannels, excuse me, we can get better performance. On the other hand, if we have smaller subchannels, we can allow more end user devices to report on each iteration. So there's a trade-off in terms of number of subchannels, and you can see that there's kind of a sweet spot from this chart here on the left. You can see that there's kind of a sweet spot for the number of subchannels for a given type of scheduling algorithm. I'll just show here some actual machine learning results just to underscore the fact that the scheduling protocol matters. So this is looking at a case where we try to, we're training a support vector machine on MNIST data, which is handwritten character recognition data. You see the parameters here, 10,000 sample points on 100 devices. And at each time, we're going to be able to select 20 for aggregating. On the left, we're showing loss, which is, I think, mean squared error. On the right, we're showing accuracy, which is % correct. And you can see that in this case, round robin, this is a case of a low decoding threshold. I don't think we put it here, but you can see that on the left, round robin does indeed perform much better than random scheduling. Many fewer rounds are needed to get down to low loss, and also up to high % correct. So the scheduling matters. It matters theoretically, and it also matters in real machine learning application. So a question we might ask is, can we optimize scheduling? And the answer is yes, we can, at least in terms of one metric. And the metric that makes a lot of sense here is the age of information metric, which has been developed for looking at situations where the timeliness of information is an important factor, in addition to the quality of the or fidelity of the information that we receive. So here we can think about age of information as being defined in the following way. For a given end user device or device I, during each communication round, if the device is selected, the age of its information drops to 0. Otherwise, the age of information increases by 1. So we have an indicator, a selection indicator. So SI of T is 1 if the ith device is selected in the tth round to be up to upload, and it's 0 otherwise. So if S goes to 1, the age goes to 0. If S is 0, the age just iterates by 1. So we can set up a problem where we can look at this optimization problem. Here we're just going to look at, we're going to forget about the role of interference here. We're just going to look at one access point to focus in on this optimization problem. So again, we have K associated end user devices and N subchannels. And here we're going to allow the end user devices to select more than one subchannel if they want to. Okay, so there are more degrees of freedom here than just which end user devices are going to be selected. So we can set up a design problem where we try to minimize the average age of information. Remember, I of t is the age of the information of end user device I at time t. Si of t is a selector for that end user device at time t. F alpha is just a weighting function for the time, standard one, before the age of information. And then we have several constraints. We have a rate constraint, which plays the role of the, if you will, a role similar to the role of the SI&R threshold and the other model that I gave you. There's a total power constraint, and there are channel constraints. There's only so many channels. And so the total number of channels in use is upper bounded by n, basically, and so forth. And so what I'm going to talk about here is basically in another Icassp paper, which you can hear later this week, which is shown here. And so I'm not going to go into a lot into the detail because you're going to see, you can see some of the details of this in another paper. So anyway, we have this model. It turns out that this computational problem is fairly low complexity. It can be solved in polynomial time. So at each iteration, we can solve this problem to decide which end user devices should be chosen for upload at that iteration. And when we do that, we see that we can get improved performance over another fairly reasonable type of scheduling algorithm called maximum pack, where at each time we try to pack in the maximum number of reporting end user devices as we can. So here, wireless round robin is the scheme I just described, where you minimize the average age. Maximum pack I just described. On the left, this is a case with high rate threshold. On the left, we see loss. Again, wireless round robin is much better than maximum pack. And on the right, we see percent correct. And again, with the same thing. This is the same problem we looked at before, where we're training a support vector machine on MNIST data. We can also look at low rate threshold, and we see very similar things. Loss is better for wireless round robin, and percent correct is better for wireless round robin as well. Okay, so I'm going to come back in a minute. I'm going to turn this over to Nir now to talk about uplink compression for federated learning, and then I'm going to come back later and talk about decentralized learning. So I'll be back.
Hey, this is Neil again, and I will discuss another relevant challenge of federated learning, which can be naturally tackled using communication tools. Now, this challenge stems from the fact that in wireless communications, and particularly in cellular communications, the upload link is typically notably more limited in terms of throughput compared to a downlink counterpart. Consequently, if in federated learning, the users are required to convey large volume of model updates repeatedly to the server, they must compress it before doing that. Now, this problem has not been overlooked in the federated learning literature, and there are two main approaches to compress the model updates before conveying over the uplink channel. The first family of method can be modeled as sparsifications. Sparsification method imply that instead of sending complete set of model updates, we're just sending a subset. So this can be just selecting a random subset, like by applying some random mask. It can be a subsampling of some random rotation of the model updates, and this allows at some level to convey a portion of all the model updates while carrying out subsampling. This can also be carried out by simply taking the most dominant gradient, which is what's called top K compression. Alternatively, the other family of approaches is based on probabilistic scalar quantization. Probabilistic scalar quantization means that we're taking the model updates and we're adding noise to each one of those updates, where the noise specifically depends on the scheme we're using, and then we're quantizing each one of those model updates. And it can be using ternary quantization. It can be based on uniform quantization, which is what's called QSGD, which is arguably the leading approach for probabilistic scalar quantization in federated learning. And it can also be non-uniform quantization, which is the recently proposed natural quantization for federated learning. Now, all of these approaches aim on representing the model updates using a limited number of bits, where the presence of noise, in fact, facilitates convergence of federated learning despite the distortion induced by quantization. Now, in order to tackle this problem from communication perspective, we need to understand what is the right thing to do for such a problem based on knowledge in quantization theory, in source coding, and in information theory. To that aim, let us understand what are the requirements for uplink compression in federated learning. Now, first, obviously, what we want to do, we want to minimize the distortion induced by quantization. Now, quantization theory tells us that in order to reduce the distortion, we need to use vector quantizers. Namely, we need to take a set of samples, do some partition of the hyperspace into discrete, distinct set, and assign a digital value to each one of those sets. Now, the vector quantization is typically dependent on the distribution of the quantized value. Namely, the partition here depends on the distribution of the model updates. But in federated learning, we also cannot assume prior knowledge on the distribution of the model updates, particularly in statistical heterogenic setups. Now, this motivates the usage of universal quantization schemes. Namely, the partition here has to be fixed, cannot be dependent on the distribution of what we're quantizing. Furthermore, there's another thing we can exploit here, the federated learning setup, and this is the fact that the server and the users repeatedly communicate with one another. Therefore, the server can share a seed with the users, allowing to utilize a source of common randomness. This is actually what's exploited in schemes based on random sparsification. They are based on the fact that even though the sparsification is random, the server knows which indexes were selected. Now, based on these three properties, we can understand what one would do for such a scheme when looking at it from a quantization theory perspective. And this is what we call universal vector quantization for federated learning. It will be presented actually here in Icassp later on this week. And it's based on the scheme proposed by Zamir and Feder back in the 90s of randomized lattices. To understand how randomized lattices work, this will be the partition of the two-dimensional space into cells. Note that the cells here are fixed and each cell has its centroid, which is a digital representation. And it does not depend on the distribution of what we're quantizing. So let us assume that the model update now we're trying to convey is a vector which lies somewhere here. What randomized lattices do, we first draw around this quantity we're trying to quantize, we draw a cell around it and we randomize a dither signal, which can be treated as noise, somewhere in that cell such that the resulting value is moves from the point of the model update to this point. Then we quantize it, namely we assign it to its closest lattice point, to its centroid, and this is the value which is conveyed over the uplink channel. This is a discrete value, so it can be represented using a finite number of bits. Then, on the server side, we're exploiting the fact that there's a source of common randomness such that the server can know the dither signal to subtract it. And then what we get is a scheme called subtractive vector quantization based on randomized lattices, and it has great statistical properties. For example, for once, it achieves guaranteed low distortion, namely the distortion achievable using this scheme is within a bounded gap from the optimal distortion dictated by ray distortion theory. Furthermore, the distortion induced by quantization here actually is statistically equivalent to additive noise, which does not depend on what we're quantizing, implying that the fact that the model updates are afterwards averaged by federated averaging inherently mitigates the quantization error. And this can actually be proven analytically. For example, if these are the weights at a given time instance, t plus tau, and these are the desired weights which one would have received in conventional federated averaging without any quantization, we can actually bound the distance by a term which depends on the squared step size and this sum here, in which recall that those alpha k's are the weighted averaging coefficients of federated averaging. which implies that if we're just doing averaging, namely if these are just 1 over k, then this term here decays as 1 over the number of users. Namely, the more users we have, the less quantization error is induced by this scheme. Furthermore, we also know that in federated learning, the step size typically decays with time. And actually, for statistical heterogenic setups, it is essential for the step size to decay on time. So this implies that this bound here also decays in time when it's in federated learning setups. So the distortion, namely the gap between the weight we are recovered by the server and the desired weight recovered by the server, can be actually mitigated. It actually grows smaller with the number of users and with the step size as federated learning progresses. Now, the gains are not only translated in terms of quantization distortion, they're also translated in terms of the convergence of the overall algorithm. And it can be shown that for smooth and strongly convex objective, the distance between the expected objective achieved using this vector quantization scheme with federated averaging and the desired one, the minimal objective, can be actually bounded by a term which grows as 1 over t, which is exactly the same, or at least the same order of convergence as that achieved in unquantized federated learning. Now, these theoretical gains of this approach are also translated into are also observed numerically. And here we consider 2 scenarios. One is when we're training a single hidden layer network over MNIST data, and here we're training a convolutional neural network over CFAR data. And for both cases, we see that the black curve, which denotes the convergence, the accuracy versus the number of iteration when utilizing vector quantization, when utilizing universal vector quantization compared to utilizing QSGD, for both cases, we see that it both converges faster and converges to a more accurate model. And this also when you don't use vector quantizers, when you use scalar quantizers, but you utilize this approach in which the server also subtracts the dither. So the gain here is twofold. One source of the gain stems from the usage of subtractive dithering, the fact that the server can subtract the noise added prior to quantization. And the second gain, the more dominant one, stems from the usage of vector quantizers. And this is universal, and it's applicable here for those non-synthetic data sets in which are very hard to model using statistical tools. Now, these numerical studies and the corresponding analytical study demonstrate one example of a challenge existing in federated learning, which can be tackled efficiently using tools from communication and information theory.
Hello, this is Vince again. Now I'm going to talk about another way of using a wireless network as a platform for machine learning, namely decentralized learning. And you may remember from what I said earlier that in decentralized learning, we don't have any kind of access point or other aggregator in the machine learning algorithm. The learning is going on only on end user devices. But they may be sharing information with one another in a peer-to-peer fashion to help the learning. And that's what I'm going to talk about now. So just a way to motivate this, we might think about Internet of Things kind of applications, which of course are ubiquitous into types of applications that where they might arise. But some of the salient characteristics of the Internet of Things are, first of all, massive connectivity. We're interested in high energy efficiency, which means we may not want to transmit very far over network in terms of network distance, low complexity terminals, light infrastructure, and so forth. So this is, for example, we may not have an access point per se that we can transmit all data through, and so forth. So some of these characteristics of IoT are ones that might motivate the kind of decentralized learning that I'm going to talk about here now. So to talk about decentralized machine learning, first of all, I want to back up and look at a general model for distributed learning. This model involves looking at learning in the terms of a bipartite graph. And one part of the graph consists of training examples or exemplars. So a training example is basically if we think about we're trying to train a model, we have input to the model X and output of the model Y. And we have examples of those inputs and outputs, and we'd like to do something to train the model that maps X into Y. So that's basically the machine learning problem that we're trying to address. So we have a training database of N samples, and this is one part of the graph. And then we also have learning agents. So they could be smart sensors, for example, or they could be access points in a general model, or anything in the cloud. And we have M of those. So this is a model that, and then there's connectivity between the two layers of the bipartite graph. So a learning agent is connected to a training datum if that learning agent has access to that training data. So this describes the learning agents and the data and which agents have access to which data. So there's some specialized cases of this. Centralized learning is one special case. So you have one learning agent and it's connected to all the data. So that's centralized learning. Federated learning is another example where you have a small number of learning agents connected to a large training database. So the training database would correspond, say, to the end user devices. And then the learning agents are or access points are connected to their own devices in their own cell. Or you can think about decentralized learning, where there are the same number of learning agents as there are training data. And in fact, the learning agents are the data collectors themselves. And that's what we're going to talk about here. So in that case, M equals N. So now one natural way to do learning when you have this bipartite graph model is to think about local learning. So you have learning agents connected to data. So each learning agent has some data points and it can simply learn a model from those data points. So for example, if we think about kernel regression, kernel learning, we can think about trying to learn a model, a function f that maps X to Y. And we can do that individually from learning agent to learning agent using whatever data is available to each learning agent. And that's called local learning, basically. So that's a very simple and obvious way to try to take advantage of this model. On the other hand, it turns out that local learning is locally coherent. And what that means is the following. If two learning agents share a training datum, but not exactly the same group of training data, they're going to learn different values of the mapping F that maps X's to Y's. So when those individual F's are applied to, say, X1 to a common data point, so here I'm thinking of F1 and FM sharing the data point X1, Y1, F1 hat, the learned function for F1, for agent 1, may not agree with FM hat and when applied to X1. So that's called local incoherence. So even though they're training with the same single data point, their other data points are different and they're going to get different values for the target on that shared data point. So this is local incoherence, and it can be shown that local incoherence is not optimal. That is, you don't get the overall best fit of learning when you do that. So the nice thing about local learning is that it requires only local communication, but it leads to local coherence, which is undesirable. So we might ask the question is whether agents can collaborate to gain coherence while retaining the efficiency of locality. And the answer is yes. And the answer comes through this paper, which is actually more than a decade old now, which appeared in the Transactions on Information Theory in 2009. And let me just explain that briefly. So we can look at a collaborative algorithm where we do maintain locality, but we have a way of getting around incoherence. So let me just describe this algorithm briefly. So we have, in this case, we have 4 learning agents. The first one is going to train on its data. And then when it's done training, rather than just moving on to the next agent, the estimated targets from learner 1 are going to be written into the training database, overriding the actual targets. So F1T of X1, which is the estimated target for training data 1, is going to be written at time iteration T from learner 1, is going to be written over Y1. Then we're going to move to training agent 2, which is going to do the same thing with its data, learning its version of F, and then writing over the targets in its data and we're going to iterate around and around until we get to convergence, okay? And it turns out that by doing this, we get global convergence to coherent relaxation of the globally optimal solution, that is the centralized solution to this machine learning problem. And you can prove that by using alternating projection, so it's not even that hard to prove, actually. So here we have we only need local communication, but we can get basically the best performance that we can get, and we can get a coherent solution. But we can just look at an example of this. Here's a case where we have 50 sensors lined up along a line between -1 and 1, just randomly deployed. The sensors are going to, each sensor is going to observe a function of its location, xi, plus noise. We'll just assume the noise is IID normal 0, 1. In this case, the function f is going to be linear, so this is a very simple problem. And then we're going to let two sensors be neighbors, or two learners, if you will, be neighbors, if they're physically within R of one another. So R is kind of the radius of a neighborhood in this case. And the sensors are going to do kernel learning, and they're going to apply a linear kernel. So this is a fairly simple machine learning problem, but it does illustrate what's going to happen here. So if you look on the right, we show test error versus R, so versus the size of the communication neighborhoods for each sensor. And down at the bottom, there's a solid of this curve, there's a solid line, which almost is at 0, which is the fitting performance of centralized learning. And here, since we have a linear kernel, a linear regression function, of course, it's going to be a very good fit. The dotted line, the one at the top, is local learning. And you can see here that the radius R has to be quite large in order to get close to that centralized learning. In fact, you almost have to have a large enough radius that all the data is in the neighborhood of each other. On the other hand, if we do SN train, which is the dash dotted line, that's the algorithm I just described, you can see that with a fairly small neighborhood, R equal 0.2, we're already down to the performance of centralized learning. Okay, so you can see that this collaborative learning algorithm is actually quite powerful in maintaining the advantages of locality while getting a pretty good performance out of the learning algorithm relative to purely local learning. I want to talk about one other topic in this area, and then I'm going to wrap up the tutorial. First of all, this has to do with a different learning problem, which is reinforcement learning. Now, reinforcement learning is not really a problem of minimizing a function through learning. It's really a function of finding decision and control strategies without a model in Markov decision processes. And a particular type of reinforcement learning is Q-learning, which is trying to update a Q function, a utility function, iteratively, seeking to converge to an optimum to find a decision strategy or control strategy that gives us the optimum utility. If we have a centralized data for reinforcement learning, the update is typically performed by gradient updates, okay? On the other hand, in a distributed setting where we have decentralized learners, we can't really do a centralized gradient update, so we have to do something different. But it turns out that in an algorithm that's described in the paper that's shown here at the bottom, which appeared in the Transactions on Signal Processing in 2013, in a fully distributed setting, we can in fact find an algorithm that does achieve global Q values under certain conditions on connectivity of the bipartite graph that I showed you. And in particular, in a fully distributed setting, at each agent, the Q function is updated not only by using a local gradient update in a classical way, but also trying to achieve a consensus among neighbors. So you have two parts of an update, gradient update plus a consensus among neighbors update. And if we do both of those updates and we have the right connectivity, and we choose the tuning parameters of the iterative algorithm in the usual way, then we can get convergence to global values. And so we don't really need centralized reinforcement learning under these circumstances. So just to show an example, this is a very simple example of reinforcement learning. We have 40 learning agents. The states are binary, the actions are binary, Connectivity, it depends on the two nearest neighbors are your network or your neighborhood. And on the left here, we look at the Q factors, of which there are 4 here because we have binary states and binary actions for a typical agent, for centralized and distributed iterations. And you can see over time, these both converge to the same thing. So we're getting centralized performance out of this decentralized algorithm. On the right, we've chosen 10 agents at random, and we're just looking at how they achieve consensus. Again, there are 4 Q factors, and we're seeing that they're all converging together for these 10 agents. So just as in the case of other types of learning, when we have a decentralized algorithm, if we do it correctly, we can get centralized performance. All right, so let me wrap up this final part of the tutorial, and then I'll wrap up the tutorial. First of all, we've been talking here about using wireless networks for platforms, as platforms for machine learning. We talked about federated learning, where edge devices like access points interact with end user devices to learn common models. Then we talked just now about decentralized learning, where the end user devices interact with one another to collaboratively learn models or actions in the case of reinforcement learning. Some issues for research here. First of all, we haven't really talked much about the fact that resources on end user devices are limited. That is, there's limited computational power, limited energy storage, and so forth ability particularly on sensors, but even on smartphones. So there are fundamental trade-offs between things, like if you're using a neural network, how many layers, how many neurons per layer, how much energy are you willing to devote to learning, what accuracy do you need, and so forth. These are all things that deserve exploration. Communications efficiency, we already talked about that. The fact that we can do uplink compression is one way of achieving efficiency. Another way of achieving efficiency is to do distributed source coding, recognizing that data may be correlated from end user device to end user device. Also, we have limited data at the edge. So local data is sparse, training sets are small. We don't really have big data here. This is not a big data type problem that we're talking about when we're learning on the end user devices. So it may be useful to incorporate domain or physical knowledge into the learner. An example of a technique we might use there is deep unfolding, where we can, which is a general mechanism for incorporating knowledge into iterative algorithms. And finally, I'll just mention security. Again, this is a wireless network we're talking about. There's possible malicious end user devices. There can be adversarial training examples injected into the system. So there are issues here that need to be considered, and people are looking at these kind of problems. I didn't write it here, but privacy is another issue. We get privacy by default, at least we think we do in these algorithms, but it is true that you can make inferences about the end data from the output of machine learning algorithms. So there's still some things to worry about in terms of privacy as well. And then finally, let's wrap up the tutorial. So what have we talked about? We've talked about 2 very exciting growing areas of technology, machine learning and wireless communications. Neither of these is really a new technology. They're decades old, but they've come to be they've evolved very rapidly over these decades, and now they're quite sophisticated. There's also a lot of interactions between the two, as we've seen in this tutorial. We can use knowledge from one to contribute to the other, and that's what this tutorial has been about. There's just a multitude of new research directions, and we've barely touched on them here in this tutorial. So of course, we're open to ideas, questions, and insights from you. We hope you enjoyed the tutorial, and we thank you for your attention. Before I finish, I just want to mention that there's some other Icassp papers that are in this general area. I'm going to leave this up for just a minute so you can see what they are. I mentioned the second one here. That's that one that uses age of information. Some of the others here have been mentioned throughout the tutorial, and these are going to be presented later this week in Icassp. So I hope you'll be able to enjoy some of those. So thank you again, and we look forward to hearing your questions.